Conductors. Let's think back to conductors, neutral conductors, like a Swiss conductor, in a uniform field. A neutral conductor in a uniform field. Let's think about what would happen, because remember what was special about conductors is that charges are allowed to move. Okay? So let's start just with our uniform field. I'll draw it, this time it's better to draw it in terms of field lines rather than vectors. So I'll draw field lines for this one like that. Okay? And we're going to apply a uniform field, E, and let's call it EAPP as a subscript for E applied. Is the field we've created in space. And let's drop in a uniform, let's drop in a neutral conductor. Let's see, draw it kind of like that. A nice little cylinder that looks kind of like that. And I'll get that off there. Like that, okay? Now, we know what's going to happen is that this electric field we applied, it's going to exist inside the cylinder. There's no reason it wouldn't. You have superposition. All these electrons and protons are running around making their own fields, but sure enough, that electric field, why wouldn't it be there? And when it's there, we know that in a conductor, the charges are free to move. In a metal, if we assume this is a metal, it's the electrons that are free to move. So this little electron is sitting there minding its own business. We turn on E applied, and it's going to move. And which way is it going to move? It's going to move this way. Okay? And it's going to end up over here, a little negative charge over there, because it's going to feel a force pushing it that way. It's going to stop there because it can't get out of the metal. Right? So they're free to move within the metal. They can't leave the metal. Now actually, the thing was neutral. We moved a charge here. We have to have actually left a positive charge there. Sometimes in physics we call it a hole. There's a hole in the electron C, so we call a hole a positive particle. I guess if it started here, it left a hole here, but if there's a hole here, this electron would jump in and fill it and leave a hole here, and this electron would jump in and fill it and leave a hole here, and it would make its way down. Anyway, in the end, we draw it kind of like that. Positive particle on that end. Okay? So let's think about what's happening to the field inside the metal. So like I said, you start out with E applied. Okay? This field is being created by, say, a giant charged plane here. It exists everywhere. But this little separation, this positive and negative charge, create a field we'll call E induced, and it's probably little, because it's just one little atom and one little electron and one little lack of electron. It doesn't make a very big field. So the net field inside the material is still that way. If you vectorially sum these two, still that way. So what happens? Another free electron says, hey, there's a big field there. I'll feel a force. And it comes over here. Negative. Puts a positive hole there, makes E induced a little bit bigger. Okay? But still, the net field's that way. So another electron says, okay, I'm going over here, and which leaves another hole over there, and E induced gets a little bit bigger, like that. But there's still a field that way. And yeah, I'm going to do it again. Another electron comes over here, negative, leaves a hole over here, positive, E induced gets a little bit bigger, like that. So as you can see, you build up negative charge here, you leave positive charge there in this conductor, and it'll keep happening. And E induced will continue to grow until something special will happen here. What has happened here is that now the induced field inside the metal equals the applied field inside the metal. Okay? So, and then the field is zero. So once you make the field zero in the metal, things stop moving. Okay? So what's going to happen is charges move until I'll say until E induced, the thing you're making, equals minus E applied. Because when that happens, E total is zero. And then they stop moving. Right? This is a condition that we call electrostatic equilibrium. Or I'm just going to write it EQ, because I get tired of writing electrostatic equilibrium over and over on the board. It's similar to the mechanical equilibria you learned about, right? When all the forces are zero and everything is still, that was mechanical equilibrium. Here, it's electrostatic equilibrium. The electric field is zero and all the charges are still. Same idea. Okay? So when you're at electrostatic equilibrium, the charges don't move. Because the force on them is 0, and therefore E is 0 inside a conductor. So if we had this conductor just sitting here, popped on the applied field, the charges would immediately do this. It happens very fast. Immediately do this, create an induced field, and E is 0 inside the conductor. Okay, so that's the main thing to take away. The electric field inside a conductor will always be 0 if you let it get to electrostatic equilibrium. Let's look then at something slightly different. That was a neutral conductor. What if we have a charged conductor? Is that different? And basically, the answer is no. Let's imagine a charged conductor here. So a sphere of a conductor, and let's drop some charge on it, some positive charges. Here we go. Here they are, floating around inside this charged conductor. Well, they're going to experience a force because, due to each of the other charges. Right, the conductor is neutral, so on average, the conductor's charges don't do anything. But this feels this force due to this. It wants to go that way. This charge feels the force due to all these. Repulsive force wants to go that way. This one feels those. Those two kind of cancel. Those kind of cancel, but it feels a big one there. Goes that way. So what happens is, in a charged conductor, the charges go to the surface. Okay. So this is a charged, right? You could also do that trick where we induced a charge separation. What if this charged conductor were sitting here, and we had a neutral conductor here? Well, what would happen? Well, this thing is net positive. It would suck negative electrons there. Right? It would suck negative charges this side. It would leave positive charges on that side. But again, the charges always go to the surface. They move to make the field 0, and often they end up at the surface where they can't get out anymore. They can't leave the metal. That's as far as they can go. So in a charged conductor, you have a fairly similar situation. The charges move until E in the metal equals 0. Right? They reside on the surface, and the charges reside on the surface, even if it's excess charges. And this all assumes that we've reached an electrostatic equilibrium. Okay? So my point really is just that a neutral conductor or a charged conductor, it doesn't make a difference. It's always the case that in a conductor at equilibrium, you'll always have the field inside be 0. And the reason is, if the field weren't 0, the charges would move. Where would they move? Well, they would move until when? Until the field is 0. Right? The field has to be 0 in the metal, because that's the only way the charges can stop moving. So we're going to keep working with that idea, but definitely keep that in your head, is that the field inside the metal has to be 0.